What's first of all the basic idea of spherical coordinates? Just like with cylindrical, it's for a three-dimensional coordinate system. You got your X, Y, and Z axes looking like this, say. You got a point right there, say in front of the paper. Imagine that to be in front of the paper. Instead of its R, theta, and Z coordinates, as we would want to know with cylindrical coordinates, we want to know its rho, theta, and phi or phi coordinates. Rho, theta, I say phi, most physicists say phi, which is right. I asked a Greek professor, it's either phi, phi, but don't say for fun. Phi is what I say. Every mathematician seems to say phi, and every physicist seems to say phi. Rho is the distance to the origin. Phi is the angle downward from the positive z-axis. And theta is the angle I'd get if I projected this onto the xy plane. It's this angle right there. Word of warning. Physicists not only say phi wrong by saying phi, they switch around the phi and the theta here. They call that theta and they call that phi. Bad, 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 bad. I think that's an awful choice, but it's what they do. It makes more sense to call this theta because it does correspond to the polar coordinate theta in the xy plane, I think, and call that one phi. But the conversion equations, when you make this choice, look as follows. X equals rho sine phi cos theta. Y equals rho sine phi sine theta. And Z equals rho cos phi. Where do these equations come from? It's trigonometry. If you draw a right triangle here, for example, it turns out, since this angle's phi, that distance right there is rho cos phi. Notice it's the adjacent side for this angle. And if you call this r down here, this becomes the same as r, and you get x and y from polar coordinates. And r is rho sine phi because in this triangle here, this angle is phi. Why? Because of geometry. You got two parallel lines where I'm drawing right now being crossed by another line. Alternate interior angles are congruent. Do you remember that from geometry? So if this angle here is phi, this angle right there has also got to be phi. And r is the opposite side from that angle. That's a phi there. That's why r has to be rho sine phi in both cases. So I'm effectively using cylindrical coordinates here to help finish this. This is r cos theta, r sine theta, but r in both cases is rho sine phi. So that's how to convert from spherical to rectangular. How do you convert back rectangular to spherical? It turns out that rho is the square root of x squared plus y squared plus z squared. That can be derived from the distance formula. Rho is a distance from the origin. It also turns out that as with polar and cylindrical, tangent theta is y over x. And so you can use the inverse tangent function to find theta, being careful to think about the sign of x. It would be inverse tangent of y over x if x is positive. Think about the xy plane here. You're positive in front of the paper. and inverse tangent of y over x plus pi radians if x is negative. Back here, if x is 0, you're in the YZ plane, you got to look at the picture. If you're over here where y is positive on the YZ plane where x is 0, in effect, the plane of the paper, the angle theta would be pi over 2. If you're over here on this side, theta is negative pi over 2 or 3 pi over 2 if you prefer. And if you're at the origin, then theta is 0. Or in fact, if you're on the z-axis, then theta is 0. How do you find phi? Use this equation. Cosine phi is z over rho. I also can use that fact to say that's the same as z over square root of x squared plus y squared plus z squared. So you can find phi with the inverse cosine function. And the inverse cosine function always gives you an angle back between 0 and pi, 0 and 180 degrees, which is good enough. You only need an angle between 0 and pi radians because phi is a downward angle from the z-axis. No matter where you are, it goes between 0 and pi, whether you're over to the right here or to the left, it doesn't matter. Phi always goes from 0 to pi, not 0 to 2 pi. 0 to pi is good enough. So you can get away with always using the inverse cosine function here as long as you're not dividing by 0, as long as you're not at the origin. At the origin, technically, phi is undefined. I guess you'd say at the origin, theta is technically undefined as well, or even along the z-axis. So these are the equations you would use, and you should certainly be able to use these equations to do real basic problems of converting points from rectangular to spherical or vice versa. I'm not going to assign any homework on that, but you'll see on old exam questions, there are a few questions, at least one, maybe two, where you have to do conversions. So you should get a little practice with both the polar, cylindrical, and now the spherical. Do exactly what I've just been saying in the last 7 minutes. You can do it, okay? It's pretty straightforward. Sometimes you have to look at the picture, though. You have to think about the picture. But how is spherical coordinates used? For triple integrals to determine dv. With cylindrical coordinates, dv was r dr d theta dz, or most typically written, I believe, r dz dr d theta. Doesn't matter, but most typically you integrate with respect to z first. Here, dv is written rho squared sine phi d rho d theta d, d phi. That's the most typical form of dv that we use here. Now, these dAs and dVs and these new coordinates might seem pretty mysterious, and I think, yeah, they are. You can sort of justify them by pictures. I did draw one the other day involving a thin slice of pizza and thinking about the arc length along a circle of radius r to help me derive dA in polar coordinates as r dr d theta, which also leads to dV in cylindrical coordinates as r dr d theta dz. Though again, the dz is usually put first. You can justify this as well with a picture. It's hard to draw. Is there a picture in the book? Yeah, there is. Is it easy to interpret? No, I think it's kind of challenging. So you can draw these pictures to pseudo justify it. But it's not really a proofs. Those kinds of justifications with these pictures are not really proofs. On next Monday, we will try to justify these a little bit more rigorously using a topic that's actually not in our textbook, but will involve an extra reading on a website like before, like we had with Lagrange multipliers. But even there, we won't fully justify everything because we just don't have time. You might think if you use this, it's going to be harder because that's kind of difficult looking, but no, it often makes things easier. Let's do an example. we've got a density function equal to just z. It's in terms of rectangular coordinates. It's always the z coordinate. And we're looking at a conical region, conical solid, I'll call it, because it is a three-dimensional solid. It's filled in, bounded by, in fact, it says bounded above by z equals square root of x squared plus y squared, and below by x squared plus y squared plus z squared equals 1. I think they made a typo there. I think the other one, I think this one should be below and this one should be above. That's our solid that we want to find ultimately the mass and center of mass for. What does it look like? Would I ask you to draw such a solid? Probably not, because we haven't really practiced graphing things like this in class. We could have worked on that in a section earlier in the book, graphing things like that. The graph of this is a cone, it turns out. Let's go ahead and use Mathematica to help us believe it. I do a plot 3D of square root x squared plus y squared. Initially, it doesn't look like a cone, but if you turn it, you see it looks like a cone. In fact, if you do a region plot, yeah, this is the disk of radius 2 centered at the origin. Then it looks more explicitly like a cone. The other region is the surface with this equation, which is a sphere of radius 1 centered at the origin. I could solve that for z and plot effectively the square root of 1 minus x squared minus y squared. That would be okay. Maybe I should do that. Square root of 1 minus x squared minus y squared. And if we restrict our plot range to being smaller in the vertical direction, say 0 to 1, and maybe make some things opaque here. Maybe make this a 1 as well. Okay. What we're after is the solid between these two things, which is really, it's hard to tell from looking at this, but it's really an ice cream cone. It's the ice cream cone inside there. It's below the sphere and above the cone. I think the book got their above and below in the wording wrong. The region, the solid, is an ice cream cone. Between two surfaces. Z equals square root of 1 minus x squared minus y squared on top. And z equals square root of x squared plus y squared on the bottom. That would be difficult for you to do on an exam based on just all these words. Okay. Probably I would need to draw this picture for you, probably not by hand, probably have Mathematica do something like I just did and paste that in the exam. What is the mass of this? The mass is going to be, as always, for a three-dimensional solid, it's a triple integral over the solid. Let's call the solid R of the density function dV. This is easiest to do in spherical coordinates because this solid region is easiest to describe in spherical coordinates. Rho, theta, and phi. Rho is the distance from the origin. It goes where no matter where you are in this region between 0 and 1, the radius of the sphere. Rho goes between 0 and 1. Theta is the angular coordinate of going around that way. It goes around the horn. It goes from 0 to 2 pi. phi is the downward coordinate from the positive z-axis. It's about that big right there. That's the phi. 0 to, looks like it might be 45 degrees, pi over 4 radians. That is correct. The graph of this cone is at a 45-degree angle. Probably I would have to say that so you knew that, in case it wasn't completely obvious from the picture. So in spherical coordinates, what do we get? In spherical, again, theta goes from, well, okay, if we're going to use this form of it, of dv, I guess we want the outer integral with respect to phi. Phi goes from 0 to pi over 4. It doesn't really matter, actually, in this case, because these are all constants, so I could rearrange the order of integration pretty easily. Theta is the middle integral. It goes from 0 to 2 pi. And rho is the most inner integral. It goes from 0 to 1. Z, what does z get replaced with? This function is z. What does it get replaced with? It gets replaced with the conversion equation for z. Rho cos phi. Rho cos phi is what z gets replaced with. Yeah, that is 0 to 1 there. That is a 1 there. And then replace dv with rho squared sine phi d rho d theta d phi. Is that hard or easy to do? Well, certainly the inner integral is not difficult. You're integrating with respect to rho, and you'd get, rho to the 4th over 4. Rho going from 0 to 1. That wouldn't be too bad. Then the middle integral would be integrating with respect to theta. You don't see any thetas. It's a constant with respect to theta. You'd get the constant times theta. So effectively, you'd multiply the constant by 2 pi in this case, because the middle integral is from 0 to 2 pi. And then the outer integral would be integrating with respect to phi. You're integrating that product. That's not too hard to do either. You could do it by guessing even. You could also use a substitution, say u is sine phi, du is cos phi d phi. Wouldn't be too hard to do by hand. Let's see how it works in Mathematica. Phi goes from 0 to pi over 4. Theta goes from 0 to 2 pi. Rho goes from 0 to 1. Rho cubed times cos phi times sine phi d rho d theta d phi. Mass is pi over 8. About 0.39. If the units are grams per cubic centimeter for the density, then the answer would be in grams. Let's see if rectangular coordinates gives the same answer, and if it would be doable by hand. With rectangular coordinates, probably the hardest part after you draw this picture is realizing what the projection, the shadow of this thing is on the XY plane. That would be the two-dimensional region for the outer double integral with respect to x and y. You'd have to effectively set these two things equal to each other and see if you can rearrange appropriately to figure out what that circle is down there. Set 1 minus x squared minus y squared equal to square root of x squared plus y squared. Square both sides. Rearrange. And probably, okay, we probably would want to write that, divide everything by 2, like that, and that's squared. It looks like it's a circle of radius 1 over square root of 2, which you wouldn't necessarily expect. Let's see if it works. Doing it now as a triple integral in rectangular coordinates. along that circle that is the shadow in the XY plane of the ice cream cone, x goes from -1/√2 to +1/√2. For the middle integral with respect to y, solve this equation for y as a function of x. You get y is plus or minus square root of 1/2 minus x squared for your lower semicircle and your upper semicircle in this two-dimensional XY plane. The inner integrals with respect to z, z goes between the cone and the ice cream. Cone on the bottom, that's that. Ice cream on top, it's that. Square root of x squared plus y squared to square root of 1 minus x squared minus y squared. Z, dz, dy, dx. So this should be pi/8. No, should be not. Oh, I know my mistake, I think. Should be 1/2 in here. Is that enough to make a difference? Yay! That's right. How hard would that be to do by hand? Well, the integral is technically not difficult, but it gives you that, expand to that. We'd have to integrate that with respect to y. That's not difficult. Although, okay, yeah, okay. Yeah, evidently using those limits of integration, it simplifies to that. How about the most outer integral? Yeah, there's where our trouble is. Okay. The final outer integral would be integrating that with respect to x. Evidently doable, but not so easy. I probably would, if I were to do that one, I'd probably take me 30 minutes at least. I'd be likely to make a mistake. If we're after center of mass in the z direction, say, so this is review now. If we're after center of mass in the z direction, sometimes called z bar, sometimes called z sub cm, it's going to be the ratio of the moment with respect to the xy plane, with respect to xy plane, divided by the mass. Symbolically, the moment was represented m sub yz, and the mass by just an m, say. We found the mass to be pi/8. What about the moment? What's m sub yz? For this three-dimensional solid, it's still a triple integral of excuse me, not m sub yz, m sub xy. M sub xy is still a triple integral over the region of z times the density. dv. This density, though, is still z, and so in the end, we integrate z squared for this example. And then whatever you get for that moment would need to be divided by pi/8, the mass, to get the center of mass in the z direction. Let's think about what would happen in spherical versus rectangular coordinates here. For the moment, we have an extra factor of z. So we would get another factor of rho and another factor of cosine of phi. That would be the triple integral in spherical coordinates that you would have to do to calculate this moment. Z squared would be the same as rho squared cos squared phi. But then you'd get another rho squared sine phi, d rho d theta d phi in place of dv. So this should be the moment. If you're going to do this by hand, the inner integral, you'd have to use the trig identity. You should put it on your note card. Cos squared of an angle, I'll call the angle A, is 1/2 plus 1/2 cos 2a. It's also useful that sine squared A is 1/2 minus 1/2 cos 2a. Yes, still a cosine. Do notice if you add these, by the way, you get 1, as you should. The cosines cancel. Anyway, the moment is that, yikes. Divide that by, let's just approximate it. About 0.27, that's the moment. Divide that by 0.392699. You get the center of mass in the z direction to be about 0.69. The coordinate would be about 0.69 of the center of mass in the z direction for this ice cream cone. The highest point in the ice cream cone, by the way, has z equals 1 because it was the sphere of radius 1. The moments in the x and y direction, or with respect to the other axes, should be 0 by symmetry. I won't bother checking it with rectangular coordinates. If we were to find another moment, like in the x direction, so m sub yz, m sub yz would be the triple integral over r of x times the density, where that's z. And by symmetry, and the fact that this density function only depends on z, it should be 0. What would I need to do with this integral to change it to being x times z? Use this equation, replace x with that crazy thing. So I would get another factor of rho. I get rho to the 4th. I get a factor of sine phi, another factor of sine phi, and a factor of cosine theta. This would be the thing I'd have to integrate. Should be 0, though. 0. By symmetry, it should be 0, and it was. The center of mass, x and y coordinates for this example should be on the z-axis.